everyone. Well, let's get started with this one. So, still needed to do this, and we are off to learning a little bit more about Scala.js, Laminar, and Vite, pronounced in French. So Scala.js, as you probably know, is the Scala to JavaScript compiler, and Laminar is perhaps less well known unless you are familiar with the Scala.js environment already. So Laminar is a front-end library for Scala.js, and Vite is a bundler from the JavaScript ecosystem. So let us start with Vite, actually, and with the provided template that Vite provides us. So after having installed all the usual stuff for SBT, Scala, JVM, and Node.js, we can create an empty Vite project using npm create Vite at latest, and it creates a bunch of things. We provide a few information like a project name, and we select the vanilla framework invariant since we're going to set it up all ourselves. Once we have done that, we can cd into the relevant directory, make sure to use npm install to install all the npm libraries that are used by Vite, and then start the development server using npm run dev. And once we've done that, we can go to that web page on localhost, and we see the templates, which only says hello Vite. All right, one perhaps the most important nice thing about Vite is that it provides live reloading by default. So here in the default example, we have a template with hello Vite inside. But as soon as we open that in an editor and we change it to hello Scala, the browser immediately updates with the changes. So that is something that we will leverage in the context of Scala.js as well. So let's modify this template and really set up Scala.js now. This is our usual SBT scripts, always a bit daunting at first, but there aren't too many things that are out of the ordinary compared to an SBT script that you would see for any other Scala project. The most important aspect, of course, is enabling the Scala.js plugin. We have at the bottom a library dependency on Scala.js DOM, so that we have static types for the DOM, for the browser API. And there is one thing that we do specifically to play nicer with Vite in particular is configure Scala.js to use ES modules, so ECMAScript modules. By default, Scala.js emits JavaScript scripts with top-level definitions, but for Vite, it's better to emit ECMAScript modules. Moreover, we configure it to use a split style that will put all the dependencies of our application, including the standard library, in one module, or at least as few modules as possible. But for our application in the live chart package, we want Scala.js to emit as many small modules as possible, so that if you change one class in your project, hopefully only one or two small JavaScript files change, and that helps Vite reload the browser faster as well. But for all the dependencies, we want as few large JavaScript files so that the browser doesn't have to load, I don't know, hundreds or even thousands of small JavaScript files. So we take the previous JavaScript template and we translate that to Scala.js. The translation is fairly straightforward. We use an @main method from Scala 3 here, but Scala 2 would work just as well. We import org.scala.js DOM, and we use dom.document, and then the rest is basically the JavaScript API that you may be familiar with. at least it's no different than the JavaScript example from the start, right? And now we start SBT, we start tilde fastlink.js. So fastlink.js is the task that produces the JavaScript file, or in this case files, because we asked to have split modules from the Scala.js source code. And tilde is the SBT meta command that asks, please watch the source files, and as soon as one source file changes, rerun that task without us having to retype it. So that way we take advantage of the incremental compiler of Scala, the incremental linker of Scala.js. And then we will feed that into the incremental reload of Vite. Right? So for that, we have to connect Scala.js and Vite, and we do that from the Vite template in main.js. We import the main.js file produced by Scala.js, and that one depends on all the other modules that it needs to, right? Once we have done that, we have our hello Scala.js application in the browser. So I said earlier that the live change mechanism of Vite is quite interesting, and we can use that now in Scala.js because we have Scala.js source files that are incrementally compiled, incrementally linked, and incrementally reloaded in the browser. So that, of course, slides are not enough to feel what it's like. So for just a minute, we are going to actually see that in action. So here I have everything set up. So this is our development server running and outputting the results. And here we have our metals, VS Code plus metals editor for the Scala.js source code. And let's see this in action. So let's change that to hello ScalaCon. I save, and it updates automatically, virtually in real time. I mean, it takes, half a second or something, which is pretty decent. All right, so let's continue from here. Now that we have our Laminar, our Scala.js application all set up for live reloading, we don't have to deal with Vite anymore, nor with JavaScript in general. We are only going to work within Scala.js, and we are now going to introduce Laminar as our framework instead of using directly the DOM API. So for that, we changed slightly our build SBT. We want to add a dependency on the Laminar library. We make sure to reload SBT and reload the dev server because we have now more dependencies. Now in the Scala.js codes, we import the Laminar bootstrap boilerplate, let's say, that is in the documentation. We change our main method to call this render on DOM content loaded, which is the entry point of Laminar. You give it first a reference to a DOM element in which Laminar is going to set itself up, and you give an element, so an element being a Laminar element, and you construct Laminar element using typical Scala tags-like syntax, so using function calls to create various kinds of DOM elements, right? So we create a div, and we have children inside, an h1 and an a-link. And then for attributes, we use the syntax, name of the attribute, colon equal, and then the value. Now, I need to introduce how we are going to represent our data model. So we are going to build a small bar chart with labels and values, nothing fancy. So here is how we would represent that in our model. So first, as pure Scala data classes, we have a case class data item that has an ID, a label, and a value. So the label is just a string and the value a double. Nothing fancy there. The ID is an instance of a final class data item ID. that we will use later for identifying which element, which item we need to change when we edit a label or a value in the UI. Now, what is more specific to Laminar is the data var. So instead of having a global variable, which is a list of data item, we have what Laminar calls a var. So that is a mutable container for ideally an immutable piece of data that we can propagate through transformations and through the UI elements, right? So we initialize it with a list with one data item for demo purposes, and we create a signal out of that. We'll see just in a moment so this is the read-only view of the data var. And we also define two methods, add data item and remove data item, which use data var.update to schedule an update of that var. And so we give it a function that takes the previous value and returns the new value. We cannot directly mutate a var. We only schedule changes that will happen on the next event loop tick. So let's see a little bit more, let's visualize what vars and signals are, because this is really the core of how Laminar works. This is also the core of what is known as functional reactive programming. So it's like functional programming in the sense that we mostly manipulate immutable data that we transform using maps and filters and whatnot. But it's reactive, so it reacts over time. If something changes somewhere, then everything that derives from that is automatically updated. So here we have an example. I create an int var, which is a var containing 1 initially. I also create a signal view of that int var. And then I also create a × signal, which is the int signal map _ ×2. So you can see a signal as a signal of int here as a collection of ints, like a list of ints. That's why you can map on it and filter on it, except it's not indexed with an index. It's indexed with time. So as time progresses, the value will change and the signal will change, and then derived signals built with map and filter will also change their value automatically. So if we start with 1, for int var, int signal contains 1 and ×2 signal contains 2. Then I send a first update to the var, saying to add 2 to it. So now int var is changed to 3. Int signal automatically reflects that new value 3, and ×2 signal automatically turns that 3 into a 6. If later I do another update with ×3, I can go from 3 to 9, and again, all the data propagates through the various signals that are built from there. Now, we can use signals as part of our UI directly. So that is really important in Laminar. Like we use signals as the data that we render as part of our UI elements. So here we render the table of data. It's not yet a chart, it's just a table. It has a table head, but the important part is the table body. And here we create one signal for one child for every item in our data table. So the way we do that is with this Laminar sort of keyword children, followed by the left arrow, and then a signal of a list of elements, right? So data signal, remember, that is a signal of list of data item. So we call map on the signal. So data is a list of data item. So I then called map on that one to turn every data item into a UI element that renders it. And so children receives a signal of list of elements, which it renders dynamically. Every time we update something, the UI will automatically reflect the changes. Additionally, we add a plus button to add a data item and a trash icon on every row to delete a particular item. Note that we use the ID of the item to identify which one we want to remove. So let's see that in action, and not to make any mistake, I pre-recorded those videos for you. So here it goes. This is our table initially, and we can click plus, and that adds new data items to the data, and the table automatically renders. We can also delete elements, and again, the table always reflects the latest state of our data table. Now, there is one thing that doesn't quite work here, is that if we select some parts and then we modify something else, we lose the selection. Why is that important? I mean, it's just, I mean, you wouldn't expect that, but it's really a symptom of something deeper, that every time one element of the list changes, we rebuild the entire list of children, of UI elements. That's not good, right? You want to preserve the UI elements for the items that didn't change. So let's see how we do that. So why do we have that problem? So remember, so we created this children list as a signal of list of UI elements. And data var initially is a list with one item, whose ID is ID1. And so it renders to a list of one data item for the children. And we call that one R1. It's the rendered one. But then when we add an item to data var, we now have a data var with an ID2 and ID1 and ID2, but that gets remapped to an entirely new list of rendered item. So we lost R1, and instead we now have R2 and R3, which are two entirely new UI elements. We don't want that, right? We want to reuse R1 for the item that did not change. So in fact, this is Laminar, of course, it's a recurring problem. So Laminar offers a direct solution to that problem. It's called split here. So what we do is we take our data signal, which is a signal of list of something, and we use split. We give it a first function that returns a key, an ID for the elements, so that it can tell which elements are the same as before and which elements are new. And for each of those, we call, as before, a render data item, but this time we receive a signal of a single data item. So that means that render data item will have to now work with a signal of data item. But what we get in exchange is that now when we update and we create a new element ID2, we literally reuse the previous R1, which is not re-rendered. Okay, so how does that translate into our application? So we define, we introduce this data signal.split to define the list of children's. And as I mentioned, render data item now has to take a signal of data item instead of a single data item. That means that the text inside the TD, so the cell element, needs to change dynamically if the label or the value of the item changes. So we transform the signal of data item into a signal of strings by using map on the label. And we feed that again with the left arrow to child.text. So this is again a laminar keyword of sorts that says the text of this element will be taken from a signal of strings. So every time the item itself changes, its label will change, so the signal of label will change, and then the text of the UI element will change automatically. We can see that in action and see the difference in behavior. So this is the same application as before. We can add an element, all right. But now if we select something and we add another element, the selection is preserved, which is really, again, a symptom that the element itself was kept. Again, if we select something in another element and then we delete even a previous element, the selection is preserved as before. All right, let's move on to the next step in building our application, because a table, text table is not much fun. We'd like to have a bar chart, right? This was our goal initially. So let's do that. And for that, we are going to use chart.js, which is a JavaScript library that renders all sorts of charts, but in particular, bar charts. So chart.js is a JavaScript library. To use it conveniently from Scala.js, it's better to use static types for it, so static facades, as we call them. And those types exist. They exist, but for TypeScript somewhere. Fortunately, we have this awesome project from a contributor, which is called Scalably Typed, which will reuse TypeScript type definitions and translate them for Scala.js. So let's see how we set it all up. We first have to install both chart.js and Scalably Typed in our project. So in green, you see the Scalably Typed related stuff. So we have a new SBT plugin. We need to add a dependency on the TypeScript compiler for development, because Scalably Typed is actually going to use the TypeScript compiler to extract the TypeScript type definitions. And we also enable the SBT plugin in our project. For chart.js, we have the yellow highlights. So we add a normal dependency on chart.js, and in the dev dependencies, we add a dependency on the TypeScript type definitions for chart.js. And that is pretty much all we have to do after having reloaded and regenerated everything we needed. Now we get types right from our Scala.js code. So we can import typings.chart.js.mod.star, which is a little bit of Scalably typed syntax, let's say. And we now want to embed that into a laminar component, into a laminar element. So we define a canvas, which is a laminar element for a canvas. We set up a few properties, and usually we don't have to deal with mount things, but since we are embedding a component from another library into a component of laminar, this is one of the use cases for unmount callback. So that provides two callbacks, one that will be called when the element gets into view, let's say, and one when it's removed. Within the mount event, we get a reference to the HTML element that backs the laminar element. And then we use chart.js, the chart.js API. I don't want to dig too much into it, but in particular, we select the type of chart that we want to render as a bar chart. And then we have a bunch of options to configure it the way we want. Now, we also want the bar chart to reflect our data from our data signal. So here, instead of asking a UI element of Laminar to pull data from a signal, we have to tell the signal to push changes to an external thing, in this case, the chart.js library. So that is what the right arrow is left for, is used for. So we have data signal on every change, call that function with the new data, and then we have standard Scala manipulations to turn that list of data items into the way that chart.js expects data to be formatted, in a sense, I mean, to fit into its data model. So we turn the labels into a JS array of strings, and we turn the values into a JS array of doubles, and then we explicitly call chart.update for the chart to re-display the changes. So again, we can see that in action. So now we have our chart, which is initialized with our initial data. That's automatic. And if we create new elements, the chart automatically updates and renders the new values. So when we add and we remove elements, everything is displayed in real time. And we did not have to do anything more to set up for this to work. The only thing we did to connect Laminar or signal to chart.js was what we saw before, just the right arrow. All right, so we have one last aspect to cover, because currently we can create random elements and remove elements, but we don't yet have any way to specify ourselves the labels and values, so that's not really interesting. So now we're going to enhance a little bit our table with inputs so that we can change the values. So recall that we configured our rows of the table using child text, a left arrow, and then a signal of strings coming from the label. So when the signal changes, the text changes as well. But now we want a two-way binding of sorts between the signal and an input. So we're going to elaborate that into an input element of HTML with a type text. So that is a normal edit box, right? And we specify two directions of data transfer. The first is more or less as before. Instead of child text, we have value, but we have value, left arrow, the signal of the label for the item. So when the signal changes, the value of the input changes as well. But now we also want the other direction. So we use the onInput element of Laminar. We call map to value, so that instead of having a signal of events, we only nail it down to the signal of new values, which are strings. And again, we use this right arrow to push changes into our model. So now we have a function with a new label, which is a string, and we do Scala stuff to identify the right item, the one that has the right ID, and transform that one, create a new item with a new label, change that in the list, but keep all the other items. I mean, it's a bit of Scala manipulations, but nothing that is specific to Laminar per se. Now we're going to do a little bit of refactoring, because this is going to be a fairly common pattern, especially in our application. So first, a pattern that is common in Laminar applications in general is having an event. We have a new value, and then we want to update a var using the previous value for the var and the new value coming from an event. So the previous value data and the new label. So that is a common pattern in Laminar. So actually, Laminar provides this updater function on a var. So we can directly use data var.updater that takes now a function of 2 arguments, the previous data and the new label, and returns the new data. So this is only refactoring. Let's do a bit more refactoring. This time, nothing Laminar specific. This is really just Scala. We want to have we have this repetitive pattern of wanting to modify one item of the list using its ID, but not change the other items. So we can extract that into a separate function. And now we are going to create this make data item updater that takes one ID, and then a function from an item and a new label. Before we had a function from the list of items and a new label to the new list of items. And now we have nailed it down to a function of one item, a new label, and a new item. And make data item updater takes care of everything else. A bit further, because now we have this, again, common thing here. We have an input whose type is text, and it takes its value from a signal. And also when it gets a new value from the UI, it pushes it to some observer in Laminar, to some function that will update the model. So again, this is a fairly common pattern, and we'd like to extract it in a function, factor it out. So let's do that. We define this function input for string, and it takes 2 things: a signal of string, which is the signal that it's supposed to reflect, and also an observer of string for if the value changes in the UI, where to push the changes, right? But other than that, we really haven't done anything to our application. We only factored out this piece of code. And in fact, what we have done here is define a component, right? Many other UI frameworks have complicated or at least have dedicated documentation about how you create custom components for that UI frameworks. In Laminar, a component is really nothing more than a def that returns an element. That is really all there is. I want to sprinkle a little bit of Laminar subtlety here. I won't go too much into detail. Now we have a UI piece of data that is both receiving from a signal and updating to a signal, and we really want to make sure that they stay in sync. And for that, it's better to use this controlled Laminar function that takes the two directions and will take care of some synchronizing subtleties. I'm only mentioning it here now because it's worth being aware that this is sometimes required to avoid glitches in the UI. But if you want the details, I will refer you to the excellent documentation of Laminar for the details. So let's see what we did so far in action to edit the labels. So now we have input elements, and we can change them. And you can see that as we change the values of the inputs, the labels under the chart are automatically updated again. All right. So, and that is really all we had to do. We connected the input to our data var. And since the data var was already connected to the bar chart, it all checks out without further work. Now we also need to change the values, right? And the values are doubles. So that complicates things a little bit because the input elements manipulate strings natively, but not really double values. So what we do is we have another function, input for double, which is this time a component for modifying a signal of double, right? And since the UI element is really more familiar with the strings, we're going to use a local var of string to connect the two worlds. So we define this str value as a var of string, and we connect the value of the input to this str value var. And then we have separately from that connection, we make the connection between the var of strings and our signal of double and observer double. So every time the value signal changes, we schedule an update to the str value to receive the string representation of that double. So that would just be new value dot toString. But it's a bit more complicated to give a good UI so that if you type in a value that parses as a certain double, but calling toString on that double gives you another string that also represents that double, but not the one you entered, you don't want the input to change to that other representation. You want it to keep the representation that you wrote. So we have a little bit of details in here to make sure that happens. But essentially, what we are doing is this new value.toString. And then we have the other direction. So every time the str value changes as a result of that, of the right arrow communication channel, every time it changes, we are going to also send a value to the value updater here, right? And again, we have some details to make sure that if the string doesn't parse, that we keep the double from before and we don't like turn the whole thing into an error state. But otherwise, that's all there is really. It's communicating between the var of string and our signal and observer of double. And that pretty much concludes our application. So now we can see our final state. So now we have inputs for both the labels and the values. We can change the labels update, and we can also change the values in real time. And the bar chart automatically updates as we edit both values, labels, as we remove elements, as we add more elements, etc., etc. So that's it for today. Here is a summary of what we covered. So in the beginning, we saw how to set up Scala.js with Vite so that we gain live reloading of our browser directly from the Scala.js source code using a pipeline of incremental things, the incremental compiler of Scala, the incremental linker of Scala.js, and the incremental reloading of Vite. Then we spent the bulk of this talk on Laminar itself, and in particular in how it uses this functional reactive programming paradigm to connect the data and the UI elements. We saw how to define what other frameworks call components for laminars, but which are really only functions manipulating signals and updaters. And finally, we took a little bit, a bit of a look at integrating JavaScript libraries in a Scala.js application using scalably typed, and also how to embed an external JavaScript component into a laminar element. With that, I thank you for your attention, and I will be happy to take questions.
All right, our first question. With the var being seen as a list indexed by time, what would filter mean?
Right. So it basically means that some of the values that come from above are filtered out and don't contribute to the resulting signal. So let's say you have a first signal, which is all the natural numbers from 0, and it updates every second. So at second 0, it's 0, then 1, then 2, etc. And then you filter that signal for the even numbers. You get a new signal. That signal will see 0 at time 0, and at time 1 second, it will see a new value coming in that doesn't pass the predicate, so it ignores it. So it remains at 0, basically, right? So for 2 seconds, you're at 0, and then when the 2 comes in at second 2, then the signal updates to value 2. So essentially, you see only the even numbers at all the even seconds. That is typically used to drop error states. And if you have an error state that comes from above and you prefer to have your UI element display the last valid value, you can filter out the elements like this.
Excellent. All right, moving on to our next question. What is the size of the final JavaScript package, including Laminar and Scala.js runtime?
So unfortunately, I did not prepare that very question, and I couldn't tell you from memory an exact number. So first, what we saw here was the development run, so where it creates many modules, fairly large. But then for production, we use a different pipeline, also with Vite, but with the production mode of Vite and of Scala.js, and that produces one JavaScript bundle. But I would say from memory, I would guess between 100 and 200 kilobytes, but I'm not really sure. You'd have to try.
Well, we appreciate you guesstimating there. That's awesome. And I think we have one final question. I don't know much about Vite. Why Vite versus the Scala.js bundler or other JS build tools?
So we chose Vite because it's a modern bundler for JavaScript things that is particularly suited to the state of the art of what Scala.js can do with the modules. So Scala.js bundler is really a wrap of Webpack, and Webpack is getting a bit old. Vite is a more modern alternative. So what Vite, the really nice thing about Vite is its capability to deal with these small module changes, that if a module individually changes, that only that gets reloaded in the browser and stuff like that. So that is really nice in combination with how Scala.js can incrementally compile and incrementally changes only the modules that actually have changed compared to the original Scala.js source code. So with Vite, you get this full pipeline of incrementality from the Scala.js code. You change a bit, that recompiles only the files that you have changed and the ones that depend on it. Then the Scala.js linker comes in and changes only the modules that need changing. And then Vite comes in and sees that only those things have changed and updates the browser accordingly.
Wonderful. Thank you for taking the time to answer the questions. Thank you for your patience with the technical issues. And Sébastien, thank you so much again for being here in your presentation today. And I hope you enjoy the rest of the conference.
Thank you. Goodbye.
Fire in retro rock.
Roger, Matt. Ready to eject.